I want to talk about Naproche. This is for natural proof checking. So it's interactive theorem proving, but hopefully using natural mathematical language. So going back to ITP, you've seen it already. What is it basically? Except this funny. So you have a mathematical text, and these mathematical texts come in various formats, just as we heard. They are input into a system which obviously has some internal representation, internal logic for that. And then there is proof checking going on by the computer. First thing was by the mathematician, and you get some appropriate feedback. Now, usually this internal logic is, there was a little change there, computer orientated, so it should be possible to implement, to run it on your computer. And the effect of that is that the mathematical text that you input also tends to be computer orientated. So the mathematician has at least have some programming idea what is going on. How do I program? How do I steer my system? So you could rather say that computer code for mathematics is entered into standard ITP systems. The Naproche approach is very different. It starts from standard mathematical practice, and we would define that to be natural. Yeah, it is natural for mathematicians to use their standard practice. And so you see there argumentative natural language in between formulas, in between symbolic material. So that is the kind of language which goes into, let's say, mathematical papers, and which is then read by other mathematicians and processed by their intelligence. So these texts are written by, and they are directed towards humans, and there is intelligence involved, intelligence in reading, because it requires natural language processing, and intelligence in understanding all these little details that are usually left out, understanding the mathematical content, and even more criteria, of course, like, oh, now I really understand the ideas or so, is also there, something which probably is very hard to emulate on computers. So we want to go in the direction of natural formal mathematics, or explore whether that is possible, namely whether one can use natural language in formal mathematics. So Naproche takes hopefully natural mathematical text written by mathematicians, and then there should be natural language processing, NLP, to turn this into a natural inner logic. And although we are sort of talking around these things a lot here, let's say the accepted mathematical logic in mathematical practice is first order logic with its extensions, let's say, towards set theory. And then this, in the Naproche system, this first order logic representation of your original text is then processed a little bit, and it's mainly given to outside automatic theorem provers to check the first order correctness. And again, you should get feedback in appropriate form. So the NLP traditionally is done with a formal grammar and parser. So these two intelligence things that we looked at, namely the reading and then understanding the argument, both these things might be done these days with different methods, with language models or so, but Naproche, due to its sort of history, is working with classical methods, and so we just use standard formal grammars and standard parsing. And for the proving task, for the understanding task, we use first order ATPs. So when you have a formal grammar and you want to parse it, then what is accepted is a controlled language, controlled by the grammar. It should be a controlled natural language. And what we do is that we have inherited from a previous project a language called Fortel, Formula Theory Language, and extended that. And we have also written a LaTeX dialect for it, so that this printout that we heard about into nice typesetting is possible. So Fortel, in a sense, is in LaTeX and allows mathematical typesetting. And then as first order theorem provers, we use E or Vampire, and you can switch between them. So here's a link to the project. So Naproche, GitHub.io is the general web page there, and you can open it, and we can already see on the first page just a snippet of text, namely Cantor's theorem that power set is bigger than the set originally, and we saw this argument already, and this is how it should print out. Yeah, and it should print out in a way which you might find in a textbook. Of course, if you see many of these Naproche texts, you see that they are, again, pretty formal, because there's a lot of sort of similar constructs linguistically or so. But we are not saying that this is sort of literature, but it's sort of natural in the sense that you can read it nicely. All right, we do this whole thing within the Isabelle proof interactive development environment thing, Isabelle PIDE. So Naproche, when you download the latest Isabelle, would be included there. And I'll demo that. So concerning the text about the power set of a set, that it's bigger, what you have to put in is, well, you put in a long thing, but here is a snippet from that, sort of the end of it. It's a LaTeX, rather standard LaTeX, which you mark by begin Fortel and end Fortel to be a Fortel part of your text, so you could have other things in a literate programming style around it. And then what is in this here, typesets to the right-hand side here. So it's basically what we've seen on the previous slide. And you could also enter this into Isabelle in the right data format, and then Isabelle sees, oh, this is a Fortel and Naproche file, and I have to run the Naproche checker on it. So we'll see this in action soon, but of course there's always a risk with these demos. So let me just show it to you statically first. So what we have here is a file which is called, you can see it right up there, cantor.fortel.tech. And if Isabelle, the standard Isabelle these days, enters or has in its editor a ftl.tech file, then it starts the checking, which you then can, for example, observe in the output window here. The Cantor file is one of the examples. You can see the file browser on the left-hand side, one of the examples that comes with Isabelle, and it's this one. So you put it in your editor, it immediately starts checking, unless you sort of disable that, and then you get your output, and hopefully something should be successful. I'm not quite sure why there are so many successes here, but this is only part of the success, and if you would scroll down, hopefully you also see the checking success. Okay, I now would like to demo that to you, And let's see how this works. Yeah, I have this little problem that somehow the mirroring of the screens doesn't quite fit, but hopefully I can reduce the font size a little bit so that I can get more on the screen. Let's see. Yeah, all right, so here's our Cantor file. And ideally, should scroll down. I would like to show you more of this file. And you can see here that around these formal bits, which are sort of the officially formal things, I can put other LaTeX stuff to make this into a mathematical article. At least it's called document class article. And then I use just things for typesetting. There is a Naproche style file so that it prints out with the formal things with the gray background. And then things start. And there's just sort of informal talking, so to speak. And this goes on. And we get to the real things, so to speak. So we read in certain preliminaries. There are preliminaries on sets and other stuff that we want to be there. And certain other definitions have to be there. For example, for some reason, I mean, I don't know the prehistory of all these texts or so, but somebody defined here a function of x here, which means just that the domain of the function is x. And then we are talking about surjections in connection with Cantor's theorem, etc. So we can, in rather, let's say, mathematical ways, define new notions on the fly. So this is sort of the natural language power of the system here. Let's define what we understand by a surjective function from this to that. And we can just say, let this stand for, and then it goes back to some other phrase which you can sort of pull out of previous definitions or of previous such language notation introductions, etc., etc. So it goes like this and runs automatically, and you can also see the running. Well, it went so quickly, but it's already done, but you can see this wiggly underlining here, which is the way to indicate that these things have been approved. You can see in the output window that there's some, well, it depends on what your settings are. You can see quite a lot of things. Output. There is an output window. Right, so it did quite a lot of things, translated and checked, etc., etc. And then in the end you see that in 6 seconds it went through all this. I mean, this is of course very poor in terms of efficiency because we read that others do all of mathematics in 1 minute or so. But there's a lot of things going on. Yeah, the parsing needs little time, but then we invoke, basically you could say we invoke sledgehammer for every task that comes up. Yeah? There's always things sent to an ATP. And also the type checking here is first order type checking, which is a proving task. Yeah? So they're not special type checking algorithms, but it all goes into e-proving, and all that takes time. So we come into many seconds here, and really other texts would require much more time. All right, so that's for the demo. I mean, sometimes in demos one wants to show that things are alive or so, yeah? So let's, we could, for example, make some errors here and write something like every function. And again, things start automatically, yeah? You see now, it tries to do something. The violet indicates that this is now in eProver and something takes a lot of time. I hope that we have an error here. Yeah, we have an error. And I mean, this is just a practical thing. The checking nevertheless goes on because sort of in developing, okay, I see there's an error, but I want to see whether the rest works anyway. It will, nevertheless, note that there is an error. You see the red, you see the exclamation mark, and on top of that, there should also be a rather visible arrow bar at the end of it. Yeah, right. So there's life in the system. This was not an empty demo.
But it can't tell you what the error is. Like, oh, you can't, you're existentially discharging or whatever when you should be universal.
Good question. Yeah, right. It is just that the error is in terms that ATP, eProver, tried for the number of seconds that it had to prove this thing here. I mean, the prover task is of course there to show an existential here, and it couldn't manage that. Yeah.
So, for example, I'm working on a math paper right now with like 15 co-authors.
Yes.
How would that handle? Because different people are working on different sections that are sub-tech files, and they might define things differently to other people. Like, how would that work in something like this?
Oh, this is all a very small experimental system. Yeah. Very good question, of course. Right. Okay, how many minutes are there? 6 minutes. Okay, so let's go out of...
Yeah, so the results of these you're running this inside Isabelle. Are the results going through the Isabelle kernel, and if so, like what?
No, Isabelle is just used as the framework in which this editing is taking place, in which the Naproche software is called. And Isabelle also provides the prover that we call. We take the eProver that is embedded into Isabelle. But one could take others.
But like all the skeleton steps and so on, that's not like, oh my God. It's just a bunch of sub-goals to be set to the
Yeah. Right, if you read the output, then you would see here that what are the sub-goals generated, and they are generated by Naproche running within Isabelle, and then these sub-goals are sent to the ATP.
You do one more step in the demo and take a surjective function, make it into take a non-surjective function, because that would be the logic of this proof now. And you see where the error then pops up?
We do this in a practical session. Right. Well, it will be somewhere, yeah? I mean, that's if you... I mean, it's sort of...
What it would look like.
I just suggest, I mean, what is it doing? It's really theorem proving using eProver, right? I mean, in theory, you could prove Fermat's last theorem using eProver, yeah? By just giving the right task to it. Yeah.
Just one more question. Are the line breaks significant?
Sorry, the line breaks?
Yes. There is one task, let's say, per line.
Oh,
Latex would ignore it, but does the...
the Naproche ignores that completely. White space is just not seen. Right. Yeah, some parts of the layout play a role for the Naproche system, some not. Hopefully, this is chosen naturally. Okay, so let's go back to the presentation. I mean, we are not shy of of difficult mathematics. Yeah? So in Bonn, of course, we have to deal with perfectory things. Spaces are beyond, but perfectoid rings, for example, are done here in a longish document, and it sort of looks a bit like a mathematical you introduce your stuff, and then certain things have to be, we are still in the beginnings here, beginnings, but then it becomes more this sort of topological stuff, and so you add and add, and in the end, at least this definition, which requires some proving, right, and proving that certain type things are correct, definition of these perfectoid rings is possible. All right, but back to the talk. Talk this we had. Okay, I wanted to fill in something. I learned that we should do this sort of openly and chaotically, so why not? And so, how would I describe the Naproche system? Well, I think we can say it's perhaps a proof of concept of this idea of natural formal mathematics, or one aspect of it. It's very experimental, it's prototypical, it's very adventurous. It is also, at the moment, the system as we have it, is really at its limits when you have these longish texts. So, for example, this perfectoid rings would take 1 hour on this computer until the definition is declared correct. But we have gone in certain ways. Some, of course, lots of basic material, number systems, actually also in the way we heard this morning that let's start with the complex numbers, and then the reals are a subfield of it, and the rational numbers are a subfield also. So this is the way we set that up. Pseudo-theorems are there, some infinitary combinatorics from rather difficult set theory, 12 of your theorems. But what we found out, or what we got, is also quite a lot of experience with working with this natural language. And I would say, yeah, it is possible, but it's really challenging, because on top of all your ITP requirements, you're basically putting these difficulties of naturalness. Yeah? You want to stay in a natural language, you have to observe the Fortel rules, you have to fight the e-prover. Of course, you could put in all the little details, but then it wouldn't look natural anymore. So you have to sort of find a balance between detail and ability. So what could the future be? And of course, the future starts now and here. So what could one do? One could, of course, invest quite a lot in the improvement of the system, or indeed all the used components. Adrien Dollon, sitting in the back, he is on the basis of Naproche developing a Naproche ZF system, more set theory based, much slimmer in various ways, and to be seen how that compares. Probably more promising is to combine generally the natural language approach with other systems, because of course we go to an intermediate format, in this case first order logic, but we also had translations into other logics, or we try to go towards the lean system, so this should all be considered. Or one could say, well, all good and fine, why don't we go to some limited area like teaching, proving for undergraduate students? That could be a nice application in the direction of a Teflon. Thank you.